All right, so here we go. All right, so we're going to talk a little bit today about linearization. All right, so maybe before I dive into the examples I've got, what is linearization? All right, so what linearization is it's a way to take experimental data and use it to find some value, right? Like you might be finding the acceleration of gravity, or you might be finding the mass of a thing, or whatever. All right, and the way that you do this is by considering the relationship between two variables, okay? And you graph those two variables, and the goal is to have your graph be a straight line. And then what we do is we find the slope of that line, and the slope of the line tells us information about the thing that we are looking for. All right, so here's the deal. So you guys all know from math class that y is in fact equal to mx plus b, right? From this point forward, I'm no longer going to use m for slope because m is usually mass in this class. So I'm going to write y equals slope times x plus b. All right. So our goal is we want to write our equation so that it looks something like this. All right. So that we're going to graph two things. We're going to put some value on our x-axis. We're going to put some other value on our vertical axis. And then we'll find the slope of the line, and the slope of the line will contain information about the thing that we're looking for. Okay. Now, please keep in mind that your variable x and y can be something else, right? Like, so it's not uncommon to have on your x-axis maybe time squared, okay? And maybe on your y-axis you've got, I don't know, I'm just going to make up something, right? Maybe it's half of your acceleration, okay? So then maybe you end up with a function that looks like this: 1/2 a equals, oh, you know what? Well, whatever, it doesn't matter. Slope times t squared plus, something, right? Okay. So what you would be doing is you would actually be graphing on your horizontal axis. Instead of graphing t like we usually do, you would put t squared on there. Okay. So I think that's probably easiest to see by doing an example, which is what I will do now. All right, so here we go. So I put together this example. I'm actually pretty happy with it. I think it's a fairly good example of kind of the type of thing that you will need to do these problems. All right. So here we go. So Roy has built a fancy device which launches lab carts with a constant force, all right, from rest. I think, it does say that later. All right. So it says he can change the distance. You can change the distance d over which the device pushes the cart to. All right. So the idea is this launcher is going to push with some amount of force on our cart. He's using the device to launch a 4-kilogram cart. So the mass of the cart is 4 kilograms. All right. But he can vary the distance over which this force affects the cart. All right. And then it says, he varies the distance over which the launcher pushes the cart, and then he uses a motion detector to measure the resulting velocity. So all of these velocities are obtained by using a motion detector. All right, here's the data. So what this data is telling us is that when he allowed the force to push the cart through a distance of 0.2 meters, the velocity of the car got up to 0.9 meters a second. When he pushed it for 0.8 meters, it went to 2.1 meters a second, etc. All right. And so the problem is he doesn't know how much force is being exerted. Okay. And so what we're going to try to do is we're going to try to figure out an equation that will allow us to find that force. Now remember, the force is going to be sort of contained in our slope. All right. It might be that the slope of the line is the force, or it might be that like the slope of our line is 2 times the force or something. So we find the slope and then divide by 2 or something. All right. And there are a bunch of different ways you can do this. So the way that I'm going to do this is not the way to do it. It's a way to do it. All right. All right. So he wants to make a graph whose slope can be used to define the force the launcher exerts. So what should he put on the horizontal and vertical axes? Again, there are more than one answers for this. All right. So before I do that, let me show you what happens. So if you just plot this data as it appears here in the data table, here's the graph you get. Oh, unhid a thing that I didn't want to. So you can see that the data here is clearly not linear, right? Like there's no way that I can draw in a best fit line. So first of all, I know that if the distance is 0, the velocity is going to be 0, right? So I know that I have to have a y-intercept of 0. But no matter how I draw my line, none of those are great representations of the data, right? So what I want to do is I want to make a new graph, and instead of graphing D and V, I'm going to graph something that has something to do with either D or V here, maybe both, and something that has to do with either D or V or maybe both here. And hopefully the line that I get will be a line instead of a curve, okay? So to do this, what I need to do is I need to figure out, using my physics knowledge, what is the relationship between the distance and the velocity? All right, so I'm looking at this and I'm thinking, okay, well, the problem is about applying a force over some distance. I'm thinking about work, and the velocity is changing, which means the kinetic energy is changing. All right, so this leads me on the path of thinking this probably has something to do with the work kinetic energy theorem. So net work is equal to the change in kinetic energy, which for us means the work done by that force. The work is force times distance, right? So our thing is applying some force. The launcher is applying some force over some distance d, and that's resulting in a change in kinetic energy. But since my kinetic energy initially is 0, this is just Ke final, which is really just 1/2 mv squared, right? All right. So what I want to do now is I want to write a new equation that looks something like y equals mx maybe plus b. But I notice there's no addition here, so the odds of there being a plus b, I think, are pretty slim. Okay, so I guess the first thing I'm noticing is that we want to get f by itself. So I'm just rethinking how I did this. So I'm sorry, we don't want to get f by itself. We want f to be something to do with the slope. So our slope needs to contain this, and maybe some other constants. And then our x and y have to have something to do with d and or v. All right. So what I usually do is I try to solve for one of the two variables, either d or, I said that wrong. Let's rewind. Let me say that differently. All right. So what were our two original variables? Let me get rid of this blue because I've now reused blue twice. Okay. All right. Sorry. So our two original variables were d and v. So where does d show up? D is right here. So that's probably going to be one of my two variables, either my horizontal or vertical axis. It previously had been my horizontal axis, so maybe that's where I want to leave it. But now I'm noticing maybe instead of graphing v on the vertical axis, maybe I want to put v squared on the vertical axis. Okay, well then let's solve for v squared. So if I algebraify this mess and solve for v squared, then I end up getting v squared equals, let's see, I got to multiply by 2 and divide by m. So I'm going to get 2f over m times d. Oh, well, that looks like it works. So let's put this, oops, that's not what I wanted to do, wrong color. Let's put this on the y-axis. Let's make this be our x, which means that this whole mess here will be my slope. Okay? So if you do that, let's see. So what that means then is I already know all of my d values because they were already in my data table. But I need to add a new column. I need to add in a v squared column. So all I'm going to do is I'm going to square each of these values. Okay? When you do that, here's what you get. Get out of the way. All right, so what I did here is I just went through and squared all of my velocities. All right. So now if I make a new graph, what I'm going to do is in my new graph, like I said, instead of putting v on the vertical axis, I'm going to put v squared on the vertical axis. So now we're going to graph this column. All right. And so if you do that, here's the graph you get. Okay. And so you can see that on the vertical axis, instead of plotting my v values, I plotted these v squared values. And look at the graph it gives you. It gives you a nice straight line, doesn't it? Neat. All right. And so now I can draw on my best fit line in yellow, apparently. All right. So let's see. Remember, you want about half your points to be above and half your points to be below. So something like that. And then you find the slope of that line. So to find the slope of the line, pick 2 points that are actually on the line. They do not have to be data points. And if you use a data point, you should write a note saying this data point's on the line. So I'm going to choose this point down here and this point up here, and I'm going to do rise over run. So my rise is, let's say we're going from 0 up to 20, and that's meters squared per second squared. And then my run is 4 meters. So my slope, when you do rise over run, gives you 20 over 4. I guess I could just divide that and tell you that it's 5. And then the units you get are meters per second squared. All right, so there's my slope. So back down here, remember, our slope was 2f over m. So we just figured out that 5 meters per second squared is equal to 2f over our mass was 4. Multiply both sides by 4, you get 20 kilograms times meters per second squared does give you newtons, equals 2f, divide, and f is 10 newtons. All right. Now, to be clear, this is not the only way to do this. There's a gajillion ways of doing it, all right? But the crux of it comes in rearranging this expression. So let me show you some other ways that you could do this. All right, so, oops, it's not what I want to do. So let's take this dude and let's move it over to here. All right, let's start afresh. All right, so here's some other ways we could have done this. So when I did this, I solved for v squared. You could, if you wanted to, solve for d. All right, so I could do this. I could go d equals 1 over 2f. I guess it would be m over 2f times v squared, right? So then this would be on my y-axis. This would be on my x-axis, and this would be my slope. Okay? You could, if you wanted to. Here's another way you could do it. The way I did it before, I ended up with an equation. Last time I ended up with an equation that was this. V squared equals 2f over m times d. That's the same as v squared equals 2... it's the same as, f times 2d over m. So you could, if you wanted to, put v squared on your y-axis, put 2d over m on your x-axis, and then your slope would just be f. All right? So there's a whole bunch of different ways of doing this. But the goal is you always want to get an expression that looks like y equals mx, maybe plus b. Okay? All right, let's do another example. You know, the one thing I was thinking about as I did this, if you put on your y-axis, this is going to sound weird, if you put y minus b equals mx, then you'll never have a y-intercept, right? Just whatever this value is goes on your y-axis, all right? And I think that's actually what I did in this next problem, if I remember right, all right? So here we go. We've got another launcher, all right? So this one applies a fixed force of 12 newtons for a fixed time of 0.5 seconds. So here's the deal. So we've got, here's our little launcher. Here's our cart. Cart 1. Oh, I turned on this ink to shape thing by accident. All right, so we're going to push this thing forwards with a force of 12 newtons for a time of 0.5 seconds. Hopefully you're thinking about change in momentum, right? All right. Now it says Roy has a mysterious cart 2, which for some magical reason he can't find the mass of on a scale. For whatever reason, it is a particularly ornery cart, and its mass cannot be calculated on a scale. So here we go. Boom, 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 boom. So here's mass 2. We do not know what its mass is. We do know that both carts begin at rest. Let's see. So he uses the launcher to launch a variety of carts. Cart 1. So here's all these different carts that have different masses in kilograms. I did not label my axes. So he's going to launch a 1 kilogram cart, a 2 kilogram cart, a 3 kilogram cart, etc. from rest at cart 2 that's initially at rest. The resulting collision is perfectly inelastic, so they're going to stick together. All right. He then measures the velocity of the 2 carts after the collision. So based on this data, what values should he graph so the slope can be used to find the mass of the mystery cart? Okay. So here's what the data table is telling us, or data table if you prefer. All right. So I forgot to put units on it. So the mass is in kilograms, the velocity is in meters per second. So if he launches a 1 kilogram cart at cart 2, after the collision, they're going at 1.9 meters a second. If he launches a 2 kilogram cart, after the collision, they're going at 1.45 meters a second. If he launches a 3 kilogram cart, after the collision, they're going at 1.21 meters a second. Now, every time I look at this data, I think, wait a minute, why is it going slower? So remember, the thing that's fixed, we're not launching cart 1 at a fixed velocity. We're launching it with a fixed force for a fixed amount of time. So let's take a look at the launch of cart 1. Here's what we know about cart 1. We know it's got a starting velocity of 0, and it's going to get launched with some final launch velocity, right? Under the effects of a net force of 12 newtons for 0.5 seconds. Well, this tells me my change in momentum. So the change in momentum during the launch is net force times time, which is 6 kilogram meters a second. And since the momentum before launch is 0, that means the final momentum after the cart gets launched is going to be 6 kilogram meters a second. So no matter what the mass of the cart is, after I launch it, that's the momentum. Okay? That feels like useful information. Why do we care about all of this? Well, now let's consider the collision. Let's use red, how about? So during the collision, what do we know? Let's see. I know that the total momentum of the 2 carts before the collision has to equal the total momentum of the 2 carts after the collision. So that means the momentum of cart 1 right after it gets launched plus the momentum of cart 2 before the collision equals the momentum of 1 after the collision, plus the momentum of 2 after the collision. All right, so let's see. So this is 6 plus 0 equals mass 1 times the velocity after the collision, which is in the data table, plus mass 2 times the velocity after the collision. All right, now remember, my goal is to find M2, so that's got to have something to do with my slope. So what if I just made that my slope? What if I made this the, oh, I don't like that orange. What if I made this the slope? So if I do that, that means that this needs to go on my x-axis, and I got to put everything else on the y-axis, right? So let's do this. So I'm going to go, 6 minus m1v equals m2v. So x-axis, slope, y-axis. Okay? So my y-axis is actually going to be 6 minus m1 times v. All right? My x-axis is going to be the velocity after the collision, and then my slope will give me the mass, won't it? All right, so what I'm going to do is I'm going to make a new data table here. let me do it. There we go. Move this out of the way. So here's my old data table. And here's my new data table. So notice it's ft, which was my impulse, 6 minus m1 times v. All right. So if you graph this data table, here's the resulting graph. Oops. Put this over here. There we go. Here's the resulting graph. Oh my glob. Oh, there we go. So here's the resulting graph. Oh, look, it's a nice straight line. So what I've got here, other than a giant scribbly mess, so notice all of these numbers got plotted on my vertical axis, and then my velocities got plotted on my horizontal axis, and it gave me this graph. All right, so what I can do now is I can find the slope. So use your straight edge and draw in a best fit line. I don't know, maybe something like that. Okay, and then find the slope. So again, do rise over run, and if you do that, it looks like here my run, or my rise is 2 over 1, so it looks like my slope is 2 over 1. Do the units work? Let's see. Well, my rise is kilogram meters per second over meters per second. Oh, 2 kilograms. There you go. That was the mass of the missing cart. All right. So, but once again, there are a bunch of other ways you could do this. All right. If you had wanted to, you could have done this. I could have left it as negative m1v equals m2v minus 6. So I could have put this on the y-axis. I could have made this the slope. I could have put this on the x-axis, and then I could have had a negative y-intercept. Okay, that's basically just shifting the whole graph down 6. All right. So that's the idea. All right. Is sort of finding the relationship between your two variables and writing it so that you get y equals mx. All right. I hope that made sense. So you guys will have the opportunity to try that here in the next week or so. All right. So, oh, wrong button. Oh, go away, Cortana. I promise I'm going to stop recording.